All right, differentiability is a very important word that will come up a lot. And in its basic form, it means we have the ability to take the derivative. So being differentiable means that you can differentiate, which means you are able to find the derivative of that function. And that's going to be super useful to us because all of our work in calculus, well, a lot of our work in calculus is going to be using the derivative. And so in order for the derivative to exist, your function must be differentiable. So we need to be able to figure out what makes a function differentiable, which then lets me take the derivative to then do a calculus analysis. So when we talk about differentiability, this next one says, try to apply the limit definition of a derivative to find f prime of x if f of x is equal to the absolute value of x. So the absolute value of x looks like this, right? Our nice absolute value of xv from good old pre-calc classes, maybe even classes earlier than that. We're supposed to apply the limit definition to find f prime. So from our last lesson, the limit definition is the limit as h goes to 0 of f of x plus h minus f of x all over h. And we're supposed to do that if f of x is equal to the absolute value of x. So the limit as h approaches 0, absolute value of x minus h minus the absolute value of x all over h. X plus h goes into those absolute value bars, and x goes into those absolute value bars, okay? Direct substitution leaves us to 0 over 0. We need to keep going. Interestingly enough, a way to keep going with absolute value is to multiply by the conjugate. Usually we use conjugates when we're talking about square roots, but we're going to use it here. So let's think strategically about what we're going to multiply together. Hopefully you guys remember that the bottom we're just going to leave untouched because the conjugate was only there to help us with the numerator. So let's leave the denominator just as it is with those nice things multiplied together. And let's think about the top. I have the absolute value of x plus h times the absolute value of x plus h. Well, that's going to give me x plus h quantity squared. Because had x plus h been negative, absolute value bars would have turned it positive. Then I multiply it by itself. Still taken care of by having x plus h squared. If x plus h had been a positive quantity, I would take the absolute value of x plus h times itself and then square it. So still, x plus h squared. Our outside, inside terms are going to cancel out, and then negative absolute value of x times positive absolute value of x will be negative x squared. All right, so now if I do direct substitution, I still have 0 over 0. Really, what's the point? Well, let's see if we can get some stuff to start canceling. I'm going to have x squared plus 2xh plus h squared minus x squared in the top, in the bottom. Also, I should tell you, you're not ever going to have to prove this. This is me doing the work of teaching, right? So you can see how this comes about. X squared goes away. I've got an h here. I've got an h here. I've got an h here. So now I have this brand new limit problem. Limit as h approaches 0 of 2x plus h all over the absolute value of x plus h plus the absolute value of x. And when I do direct substitution here, I'm going to get 2x over 2 absolute value of x, because this h will go to 0. 2's cancel out, and I'm left with x over the absolute value of x. That is equal to my derivative, f prime. And if you're looking at this, if f prime of x is equal to x divided by the absolute value of x, this function, x divided by the absolute value of x, has a domain problem when x is 0, which means this domain is negative infinity to 0, 0 to infinity, because we can't divide by 0, which means that f prime, my derivative, exists on this interval and this interval only. Another way of thinking about that is I have a problem on my derivative when x is 0. Well, let's go back and look at our original function. Our original function was the absolute value of x, and I'm finding that I have a slope problem at 0. Well, on my curve, right, I'm not locally linear at x equals 0. I've got a sharp turn going on at x equals 0. So if I jump over to Desmos, here's my absolute value of x graph. I've got negative slopes, I've got positive slopes. At this turn, though, I don't know if I have positive or negative slopes. If I zoom in and zoom, I just keep seeing the sharp corner, right? It never gets linear by any means. When I go to graph the derivative, where'd it go? There it is. There's my derivative. I have negative slopes on the left, a slope of -1. I have positive slopes on the right, a slope of 1. And at 0, my blue graph, my f prime, is not defined. So because my derivative has a problem at 0, we would say that my function, absolute value of x, is not differentiable at 0 because there's a discontinuity on f prime. We're going to start thinking about continuities in different layers. All right, let's look at another one. Consider f of x equals x to the 1/3. This one we're not going to do with limit definition. You could if you wanted to, but we're going to look at this one strictly from a graph standpoint. You're going to draw this graph in your notes. So the graph of x to the 1/3 is the inverse of the cubic graph. So it ends up looking like this. That is our graph of x to the 1/3. And if I think about what finding f prime of x would really mean, f prime of x again means the slope of the tangent line. Well, if I find this slope, that's a little bit positive, more positive, more positive, more positive, 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 positive slopes, until all of a sudden I draw in a line, a tangent line, that is perfectly vertical. And what is the slope of a vertical line from your Algebra 1 days? Slope of a vertical line, we always said, was undefined. So if the derivative means find the slope of the tangent, and we just found the slope of the tangent is undefined, that means we can say that f prime is undefined at that moment. Notice that once I get past that problem, now my tangent lines are still positive, 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 less positive, but still overall there and in existence. It's just that one instant where I have a problem on my derivative. So if I look at my graph of what's going on, here's my graph that I just drew for you. And when I go to graph the derivative, my derivative, unlike the absolute value of the absolute value of x situation where I had a discontinuity with a jump, when I talk about x to the 1/3, my derivative has a problem because I have a discontinuity of a vertical asymptote. But notice that it's still only at that moment. My function is differentiable everywhere, except where f prime is not continuous. So, differentiable everywhere, f prime of x exists everywhere except where I had that problem, which coincidentally in this example is 0 also. It's not always going to be 0. Maybe that was a bad choice of example, but we'll see more in class. All right, a function with a discontinuity. So if the function itself has a discontinuity, you're going to have a differentiability problem, okay? If your function is otherwise smooth, we will have differentiability problems at corners, cusps, or vertical tangent lines, and that's because f prime is not continuous, okay? Local linearity, if you could show that your graph is locally linear, that's going to imply that you have differentiability, okay? If your graph is locally linear, your graph will be differentiable at that point. So, if my graph is differentiable, that means my graph must have been continuous. However, just being continuous doesn't mean differentiable, because we just saw this graph was continuous but has a differentiability problem at 0. This graph was continuous but has a differentiability problem at 0. So just because your graph is continuous does not mean it's differentiable. But if you found your graph was differentiable, that does mean your graph was continuous. Okay? Overall, derivatives do not exist if f of x has a discontinuity. And remember from our previous unit, we can think about discontinuities as removable or non-removable. We also could say whole, jump, or vertical asymptote. Derivatives also do not exist if f of x has a corner, if f of x has what we call a cusp, which is what we have when it kind of looks like a little bird graph, as opposed to two linears causing a corner, or if f of x has a vertical tangent. Now be careful, because up here in number 1, we talked about vertical asymptotes. That's different than a vertical tangent. Remember, a vertical tangent was where that yellow line all of a sudden was vertical. These right here will all be places where f prime is not continuous. So often students ask me, like, well, how do you know without a graph if your function's differentiable? Well, you would take the derivative and see if the derivative is continuous, and we know how to check continuity from a previous unit. Last thing to talk about, we'll wrap it up. We're going to be doing some connections between our functions f. Here's f. And what does the graph of f prime look like? There's f prime. So what you want to start thinking in your head is that if f is increasing, that means f has a positive slope, which means that f prime is positive, which would be drawn above the x-axis. That's where positive numbers lie. If f was decreasing, then f, we would say, has a negative slope, which means that f prime itself is negative and exists below the x-axis. So let's look at this example quick. F is increasing from here to here, and increasing again from here to here. And look at my f prime graph. I'm above the x-axis, and I'm above the x-axis. Versus this part, f is decreasing, and look at my derivative. My derivative dropped below the x-axis. At the moments where I had a nice little slope of 0, my derivative graph crosses the x-axis. Where I had a slope of 0, my derivative graph crossed the x-axis. So positive, negative, positive, because my original function was increasing, decreasing, increasing. And that's just a super quick intro. We're going to spend an entire month studying that, but I want you to see it because we're going to start making those connections in some graphs in the next couple days, just kind of on a preliminary level. All right, that's it. Differentiability, the ability to take the derivative. We don't have derivatives if our original function has a continuity problem, or if f prime has a continuity problem. And the reasons f prime would have a continuity problem is if we have a corner, a cusp, or a vertical tangent.